Gautami Bhaumik from University of Lille, and she will be speaking on bounds on siegel zeros. Please, Professor Bhaumik.
Okay, so thank you for all this work. So I'm going to talk about bounds and siegel zeros. It is quite possible that everyone in the audience knows everything about this question, but it is also possible that there are some people who I don't know who have come from somewhere because they don't know what to do on a Saturday and then they want to hear this talk. So I'll give you just spend a few minutes giving some details, okay, just to introduce the question. So what do I have? I have a dirichlet character chi, which is modulus of some, so this is modulus some q, and I consider the L function associated to it, which is the sum of chi of n by n power s and can be written as an Euler product. So in particular, you could have chi to be 1, and then you get the zeta function. Yeah. So of course you know all of that. So this is a very old question. This is in fact older than Riemann. It is 1837 by dirichlet, who introduced this to study the class number and the infinitude of prime numbers in arithmetic progression. So where are the zeros? The zeros, the non-trivial ones, these are between 0 and 1. Yeah. So you have a 0 here, and you have a 1 here, and the zeros are, so that's where they are. Okay, and then what happens? Where do you expect them to be? Of course, you expect them to be here. Yeah. At so if you wrote out your if you wrote out your 0 as beta plus I times gamma, the chi need not be mentioned, then the beta should be equal to half according to the GRH, the generalized Riemann hypothesis. So, and then what do we know? We know that the real zeros, which are close to real s equal to 1, this doesn't happen very often, yeah? So yeah, so if you are close to this line here, then this doesn't happen very often. So that's what I say, that these are indeed rare. Yeah, they are rare, but they're real and they are rare. Okay, so so now suppose there is an exceptional 0. This exceptional 0 is called siegel 0, and then some people have called it the Landau siegel 0, or sometimes an exceptional 0. This means that there is an exception to the generalized Riemann hypothesis. Okay, so if it does exist, then how does it behave? Then it is real. It comes once. It's unique, and it is one possible exception to the generalized Riemann hypothesis. So there could be other exceptions. So what do we know about this? So what we know about this, that if there is a 0, then all other zeros are going to be pushed away from the real axis. Yeah? This is the famous Doering-Heilbronn repulsion theory. Yeah. So what does it say exactly? It says that I'm giving it to you in the form of the way Linux stated it in 1944, because it could also be stated in the original form, but that's kind of slightly more complicated. And this is this is restatement of about 10 years later by Linnick, because during Heil-Brown, I think it was in 1933 or 34, 30. So this is about 33, 34. And then this is about 10 years later that Linnick stated this. And what does it say? That if there is an exceptional zero, beta, we call it beta, in the with this property that one minus, that one minus beta is less than epsilon times epsilon divided by log q, and epsilon is rather small, then all other zeros are going to behave for a given L function with a modulus q, such that 1 minus beta, 1 minus sigma is going to be bigger than some constant times log 1 by epsilon divided by log q, 2 plus absolute value of t. And this c that you see here, this c, this is an absolute positive constant. Yeah, so Linnick used this to find the size of the least prime in an arithmetic progression. So, so what's nice about the way this result is stated is that we gain out by a factor of this, we gain by this factor, log 1 by epsilon. Okay. And there is this result was strengthened by Bombieri, who showed that this was much later, 1987, and Bombieri showed that I take some t, which is greater than or equal to 2, and beta is an exceptional zero for sigma greater than some constant c by log t. Little t is bounded by the big T. Then there exist constants C1 and C2, such that the same 1 minus delta that you, 1 minus sigma that you see here, this can be written as C1 times two constants C1 and C2 log C2, 1 minus beta log T, and the whole thing by log T.
Excuse me, so can you just move your slide slightly to the left? So we are getting a partial, yeah.
Okay.
Yeah, that's it.
Is it better?
Yeah, so okay, it has moved a little too much to the left. So slightly, yeah, that's okay. That's perfect. Perfect.
Okay. So this is Bombieri's result in 1987. And if you wanted, you could have stated this as a density estimate. And this is, as a density estimate, it would look like this. So you could have written it like this. N alpha qt is less than 1 minus beta log q 1 plus log t by log q qt times big O of 1 minus alpha. Okay, what are all these things? So, and what is this this n? It is now the number of zeros which are counted with this n, this number of zeros counted with multiplicity. And for any L function of modulus q, this alpha is a bound for sigma. So alpha is between, so sigma is between alpha and 1, and little t is between 0 and t. Okay. So this is a density estimate. Yeah. And this is, I'm writing it the way, what the nice result that you will get if you use Bombieri's expression. Okay. So now here's a result everybody knows. This is Siegel's 1935 result. It says that if there is an exceptional 0, which is associated to a primitive character chi, which is conductor Q, and if you choose your epsilon positive, then you can find C epsilon, which is greater than a C epsilon, which is positive, such that 1 minus beta is greater than C epsilon upon Q to the power epsilon. Now, what's good about this result? Of course, it gives a bound. But what's not good about this result is that this result is not effective. Okay, so this result is ineffective. And the fact that it's ineffective, it's ineffective every time epsilon is less than half. It makes that it says that we cannot use it for many applications. However, nothing much has happened. Siegel, you see, this is 1935, which was very long ago. And seriously, unconditionally, this result stays as it is. So only possibilities are to sort of go around the story. You see, you go around and you try to see if you can put some conditions which will make it better. If you can study, for example, the zeros by some other method, for example, by looking at the value at s equal to 1, etc. Then it's these are some ways somehow to go around the problem, because essentially the theorem as it stands has not been yet improved. Yeah. So there is a version by Tatuzawa for the effect. There is an effective version of Tatuzawa in 1951. But it's a partial result, yeah. So sort of effective, yeah. But yeah, so that's why I put some brackets around it, yeah. So what do we know for these zeros of LS chi and their values at 1? This is known since forever. And what we know is that if we have, so these are closely related. So for example, if I have L1 chi is less than or equal to, L1 chi is less than or equal to some constant, positive constant times small positive constant times divided by log of Q, then 1 minus beta is less than or equal to 1 by log Q. Yeah. So that's something that's known. And using using what Friedlander and Ivanic in a somewhat recent paper, they say that they call the Heilbronn, they call it the ultimate Doering-Heilbronn property. Using that, they can show that if 1 minus beta is less than, that is in the other sense, yeah. If 1 minus beta is small, then Ly chi is small, yeah. They proved this using the DH, yeah. A certain form of this DH. There are many forms of this. So there are other applications of this L1 chi. One example that probably everybody has seen, that is that if you have L1 chi to be, if you have the class number formula for this one, L1 chi equal to pi HQ by square root of minus Q, then you get the prime number theorem and in arithmetic progression, and you get an elementary lower bound, yeah? And you get an elementary lower bound, L1 chi, which is bounded by 1 by Q to the power half. However, the good effective lower bounds are very difficult to get, yeah? You are looking for two things, it's good and it's effective. So what do? You can't quite just sit down and feel very bad about it. And so this is elementary, yeah. There are some improvements, but usually under some conditions. So I want to talk about some of these conditional bounds. The first one is really old, 1928, it's Littlewood. And this says that if you assume the generalized Riemann hypothesis, then L1 chi is bounded by, on both sides by 1 by log log Q and log log Q. And this can be, you can actually, Littlewood actually gave the constants here, yeah? He gave these constants here. So this is here, sorry. That's bad. Yeah, so you can get some constants here, half of little o of 1, and here you can get 2 plus little o of 1 e to the power gamma. Gamma is Euler's constant, but only the implied constants can be, these implied constants are therefore effective, but only these can be improved. This bound is optimal because there's a result by, there's omega result by Chawla. This is 1949 and says that this cannot, it says that you cannot really do very much better. So under GRH, this is about what you can expect. There are improvements. Some people continue to improve things under some assumptions, etc., especially trying to see if they can do anything better with the constants. And so you can't do much with the GRH. So you can do what you can do. So let's see if you weaken the GRH, what happens. So that's what, here is a modified GRH. It says that if there are zeros of LS chi, then they are either on the critical line or on the real axis. Okay, this is the modified generalized Riemann hypothesis. I don't know who first thought about it. I know that this exists in a paper of Sarnak and Zarascu. And they show that if we can assume this, if we assume that all dirichlet LS chi satisfy the modified GRH, then L1 chi is bounded by some positive epsilon, for any positive epsilon, by C power epsilon log absolute value of epsilon to the power epsilon. Yeah. So this result is not effective. Yeah. This is not effective. But if you add some more conditions, it can be made effective. They show it in the same paper, that if you add some further conditions, it can get better. Yeah. So this is one way of, you do something, you change your GRH, and you can get some results. And then Friedlander and Ivanic, they say they allow some exceptions. They say that the GRH is true, which it probably is, and except for only one beta, and for that beta they give a condition. They say this beta is greater than 3/4. So I call it GRHE with exception, and then they show that if this is the case, if we assume this GRHE, then 1 minus beta is bounded by no. If I assume GRHE and if 1 minus beta is less than 1 by log Q, in that case L1 chi can be bounded by 1 minus beta log Q square. Yeah. So here, and on the other hand by 1 minus beta. But the conditions are assumed. Yeah, certain conditions are assumed. Yeah. So now I want to give you some other exception. Conditional cases. So this goes via the Goldbach problem. The Goldbach problem, as you all know, it's finding little g of n, and writing it as P1 plus P2 for 2 primes whose sum is n, and of course you see whether n is odd or even, and what is an old result in this direction? It is a conjecture of Hardy and Littlewood of 1923, old, so 100 years old, yeah. So it says that g of n can be very nicely approximated by a singular series, which is given as the product over all primes that do not divide n, yeah. Okay, 1 minus 1 by p minus 1 square, n by log square n, and you have an n by phi n, and this should be a good approximation. This is expected, yeah. So and what is this? This can be written as, so you could also write this as, I'm just stating it because of a certain reason which you would see. So this is equal to 2 times C2. So this is the twin prime, the constant of involved in the twin prime problem, and some product here, and the same thing here. And this C2 is about 0.66. Yeah. So this is approximately 0.66. Yeah. And here, and so there are some conjectures. For example, Andrew Granville has a conjecture that the GRH is equivalent to an asymptotic form of the average Goldbach formulation for arithmetic progressions. And this conjecture has not been completely worked out yet. So, however, what is known, one of the things that is known in this direction is a result assuming a weak Hardy-Littlewood conjecture, weakening the Hardy-Littlewood conjecture. This says that there is some positive constant, yeah, delta, where such that g of n is this representation of n as sum of 2 primes, Goldbach representation. If this is greater than delta n by log square n for every integer n greater than 2, then phi proved in 2016, then if we assume this, and if there is an exceptional 0 beta for a chi which is which has an underlying prime modulus Q congruent to 3 mod 4. In that case, you can improve on Siegel's bound. You can get 1 minus beta is greater than or equal to C by log square Q. So what phi does is he gets a lower bound. He gets a lower bound using the weak Hardy-Littlewood conjecture, and he gets an upper bound using the prime number theorem in arithmetic progression. Okay. So what I want to say is that we can somehow improve on this result of phi's by assuming a condition which is weaker than phi. So here is phi. It says there exists a positive constant, delta, such that g of n is larger than that. And we can make this weaker, and we can include some other conditions more than this q congruent to 3 mod 4. Yeah. So as a special case, so this one, yeah. So as a special case, it should give phi's result. Yeah. Okay. So it's not a wonderful result. Yeah. So it's a small improvement I mean, it's not even really an improvement on siegel because it's conditional. Yeah. So what is our, because it's a result with Karin Halupzog of Düsseldorf. And we make a conjecture that if X is large, yeah, we make a conjecture that X is large. How large? We will see. And Q is greater than X by 4. Then we admit some exceptions. This is similar to what I have shown you before, that with you take GRH and then you say that it's true except for some exceptions. So I need this to assume that there are exceptions at most X by 8Q times. Then we have G of n is greater than n log square n. So for a given interval for n, which is between X by 2 and X. Okay, it might look artificial, it probably is. And but these are things we needed to be able to improve on the proof. So we assume that this conjecture is true. We assume this, yeah, Gn greater than n log square n under certain conditions. Yeah, and we need a further condition that chi minus 1 is less, chi minus 1 is equal to minus 1. Okay. And assume now that there is a beta. There is an exceptional 0. And then we can show that if this is the case, then 1 minus beta is greater than C by log square Q. There exists some such C, which is a positive constant. Now, so it is a conditional improvement on the Siegel, on Siegel's theorem. So I can give you some an idea of how the proof goes. So this proof is like it's we'll get a lower bound and we'll get an upper bound, and some nice things will happen in this. So it uses the circle method, yeah. So the proof uses the simplified circle method. So it is a simplified circle method, which uses only one modulus, yeah, and we use the prime number theorem in arithmetic progression, and then we compare. It is not very, very different from phi's proof. It is, however, it is done little bit. It's pushed to where we could push it. Yeah. So remember that Q in our condition, we had that Q was less than X by 4. So the Q being less than equal to X by 4 is still used. And then we have S, we want to find the sum. We write it as we write it as a sum for all k was an exponential sum kp by q square, and the prime is between 2 and x. Okay, and so to prove this, let's call this S1. I write my prime as P1 plus P2. Okay, P I write it as P1 plus P2. And to be able to get some nice cancellations. Okay, so this E now becomes, instead of having K of P, I have it as E K P1 plus P2 exponential of this by Q. Okay. And Q, as you remember, is less than or equal to Q by 4. So with the conditions that I have, I can get the sum of 1 for P1 and P2 between 2 and x. This will be greater than or equal to delta x by log square x. Okay. So, and then you have another sum. So then you try to get an explicit expansion. So here I have used the weakened Hardy-Littlewood conjecture with exceptions. Otherwise, you cannot get this. Otherwise, you cannot get this in our proof. I don't say that otherwise you cannot get it. I don't know. Okay. Then we get an explicit expansion. What do? We take two cases where Q is divisible by a prime and Q is not divisible by a prime. Okay. So if Q is divisible by a prime, then we not divisible by a prime, then we use the prime number theorem in arithmetic progression. Yeah. So then okay, what we can get is S1. This is equal to some m plus, here is my Ramanujan sum. Okay, Euler phi, okay, plus big O of Qx for some constant C tilde square root of log x. So what is m? M is equal to, and here comes the Gauss sums. Okay. And you get an integral to x. Okay. So this is a Gauss sum, and this is the, so now this you cannot see. So so here is Ramanujan sum, okay, and here is a Gauss sum, okay. So probably I don't have to, and then for the Ramanujan sum, I can bound it, and for the and the Gauss sum, I can use some estimates on this Gauss sum. Yeah. So if you do this, some nice things actually happen, and there are cancellations that are possible. Yeah. Nice cancellations take place. Yeah. And the Ramanujan sums disappear. Okay, which is quite nice. Yeah. So cancellations take place. So Ramanujan sums disappear. So actually, probably you don't need this. Probably you can do it directly without the Gauss sums. But well, it will not give anything new, but maybe another way, a simpler way to do it. I don't know. Yeah. So once you have done this, then you split the sum S for k equal to Q and k less than or equal to Q. And then you get S is equal to, for k equal to Q, you get this form. For k equal to Q, you get x squared by log square x. And then you get some more terms. Yeah. And what is this error like? And the error term is like, you can expect something like x squared log cube x. So it's a big O of, if you work this out, q squared by 5q squared, and so on. Yeah. So you have to choose now. So now you choose your x carefully. You choose it. So one part of this choice comes from your assumption, the WHLE, and another is to you make sure that all the results that we are using are not none of them are contradicted. Yeah. So you use that. So so when you now remember that we had this condition that chi minus 1 was equal to -1. Remember, it's not very nice as a condition, but we need it. Yeah, I mean, we need it for our proof. So and then you get this error, which I just showed you. Okay, and so that's what I mean when I say that choose x appropriately. Means neither too big nor too small. Okay, so to keep everything going. Okay. And then, as I said, you compare them, and you get the result. Okay, and I want to say that these constants all of these are effective. Why are they effective? Because what we used is the prime number theorem for arithmetic progressions. So if you use the prime number theorem for arithmetic progression, then you get your constants from there. Yeah, just as the delta that we got here, this delta for our proof, it's enough to have it just small. But I think you can go up to 2 times C. So C being 0.66, this will be 1.32. Probably you can go up to 1.32. And then you can actually effectively work out all the constants. So even if this result is conditional, at least you can get the condition, the constants effectively. Okay. So now what has happened is from phi's case, we have moved to including some composite moduli. Phi had only prime moduli, and phi also had the case. So this is a corollary of our result. It says that if you assume this conjecture, the weak and hardy Littlewood conjecture with exceptions, and if Q is sufficiently large with some conditions, which comes from your chi, then there is a beta such that 1 minus beta is large. Yeah. And so which case is phi's? Phi's is the case that Q is congruent to phi's Q is equal to P, and it's congruent to 3 mod 4. Yeah, you see that here. This is here. So this is phi. Yeah. So it follows from that. It also from this result, again, these are conditional results, as I said. So if we assume the weak and Hardy-Littlewood conjecture, if we assume an exception, so many assumptions are there. So you use Hardy-Littlewood conjecture weakened form. You use the form chi minus 1 is minus 1. And if you take the conditions of Ivanich and Friedlander and Ivanich, then that the GRH holds except for a possible beta, which is at least 3/4, no more than 3/4. In that case, you will be able to show that L1 chi is greater than 1 minus beta, and it's greater than 1 by log square q, which is a slight improvement on the Ivanich Friedlander result, but includes more conditions. Yeah. So having said all this, you are probably somehow frustrated because these results are, as you see, everything I've given in yellow, it has lots of assumptions. Hardy-Littlewood, the weakened Hardy-Littlewood, chi minus 1 equal to minus 1, etc. So is there any hope? So, okay, I should have a new page here. So, yeah, this is the time to say that I'd like to thank all of you. That is Shanoli, Anirban, Purushottam, and Shukumar Da, who is also Shukumar Das. So, and I hope that we will meet for Balu's 80th birthday. If by then maybe the situation will be better. So, so now let me say if there is any hope. So, are there any hopes? Then, so the conditions. So, so what are the hopes? Hopes are that can we find an equivalent of the weakened Hardy-Littlewood conjecture? Does it exist anywhere? I don't know whether it exists anywhere. Some kind of, and if there is an equivalence, or if something implies the weakened Hardy-Littlewood conjecture, then maybe we can say something more. Something else that I would that is irritating is this: chi minus 1 is equal to minus 1, right? This chi minus 1 is equal to minus 1. Can we forget this? So here I think that maybe if we take the g of n, if we take the g of n to be less than or equal to 2 minus delta instead of having delta times n and log square n, then maybe we get a lower bound, which is delta, and an upper bound, which is 2 minus delta. Yeah. So so this is actually morally quite close to the to a sieve parity problem, and this might be doable. In that case, probably chi minus 1, some more chi minus properties of chi, some more chi can be included in the proof, and yeah. Perhaps I should stop now. Yeah. So I wish Balu a very long continuation and many proofs and everything good that should happen to you and to people around you. Okay.
So if there are any questions, then you can unmute and ask.
I should unmute?
No. You are already unmuted. So all participants can just unmute and ask. So there is one raised hand, but please go ahead and unmute and ask your question.
There are no raised hand on even now.
I see one. I see one raised hand. Oh, no, it's gone. I think somebody just clicked by mistake.
He found the answer.
Yes.
Yes.
So if there are no questions, we thank the speaker. You can unmute and clap. That's what we have been doing. So we meet in 10 minutes for the next talk.
Can you make it a little bigger? The slides? Full screen? Maybe?
About that.
Yeah, thanks. Thanks. So what is the time in your place?
So these are all slides. Don't worry, I have slides for this year.
So what is the time in your place now? What is the time for you?
It's 1 p.m. almost.
Ah, okay. And Valentin, what is the time for you?
Oh, I'm in the
Charlie,
same time zone.
Okay.
So it's 1 p.m. It's fairly convenient.
I think for people in the US, I think it's a little difficult because Henrik was attending 4 o'clock in the morning, the first lecture he attended today, and he said that it is 4 a.m. for him.
Yeah, but I think you did a very good job accommodating many time zones simultaneously. I mean, this is not easy, but I think the way you did it is close to optimal.
I mean, yeah, if I don't, okay, thank you. But it's, I think, Anirban, the credit goes to Anirban. He's the person who was looking at all time zones and fixing it.
You know, and we also messed up with that that daylight saving hour. But I mean, now it is okay.
And speakers are quite accommodated, I would say.
My kids are talking. Wait. Yeah, I made it back in time. That's good.
So we start in 2 minutes. It's just.
I get some water. I have this dry cough and water helps.
Okay, yeah.
Okay, I'm ready. How about the audience?
Yes, I think people are joining. So let's wait for 1 more minute to allow people to join.
Okay, I cannot see the participants now because of my sharing.
Anirban, maybe we can start
Okay,
and the
sure.
participants can join.
Okay, yeah. So yeah. So okay. Let's start then. So I welcome our second speaker of this session, Professor Gargly Harkos from Alfred Rennie Institute of Mathematics, and he would be speaking on the
That's not my title. That's not my title. That's my title.
Yes, beyond the spherical soup norm problem. Yes. Yeah.
Okay.
Thank you, Professor.
So this other page I put up out of nostalgia. So first of all, big thanks for the organizers to put together this online event. I was involved in organizing a similar event in last June, and I know the huge task involved. So I'm very honored to be here, and I wish you already happy birthday to Balu. And as you can see, 5 years ago, I had a pleasure to be in Chennai in person in the celebration of his 65th birthday. And in a sense, the talk I'm going to give is a continuation, or at least very closely related to the problem discussed on that occasion, which was a subnorm problem for arithmetic hyperbolic three manifolds. So that talk addressed spherical mass forms in the eigenvalue aspect, whereas today's talk will be about non-spherical mass forms on SL2C. So my current title is Beyond the Spherical Subnorm Problem. And in fact, I copied one page from my previous set of slides, a nostalgia page from 2015, which gives you some connections and applications or kind of motivation for the subnorm problem. So why are we interested in the subnorm problem? Why should we care? So first of all, the subnorm problem addresses pointwise bounds of Hecke eigenforms on arithmetic manifolds, or more generally on quotients of arithmetic quotients of Lie groups. So pointwise bounds give rise to the subnorm, or when the points are restricted to a compact subset of the group at hand, and the restricted subnorm. And we would like to estimate these subnorms, the global one and the restricted one, non-trivial. So why are we interested? There are a couple of connections. For example, in arithmetic quantum chaos, we are interested in the L2 equidistribution of eigenforms. So if you take the absolute square of an eigenform and associate to it an L2 normalized eigenform and associate to it the corresponding probability measure, then taking a sequence of eigenforms, say with growing Laplacian eigenvalue, you would like to see that these probability measures tend in the weak star limit to the uniform distribution. And in several cases, that's a celebrated theorem. So the subnorm problem kind of addresses a complementary aspect of this problem, namely in the subnorm problem, we don't want to see very high peaks, whereas in arithmetic quantum chaos, we are more interested in the average to behavior of eigenforms. And another obvious connection, once you study the subnorm of cusp forms, you can also study other LP norms, or even more general Sobolev norm of cusp forms, and those are very interesting questions that address other kinds of value distribution of cusp forms. Now, another obvious connection is with the subconvexity bounds for L functions. A big difference being between the two problems, that in the subconvexity problem, we have a very clear understanding what the trivial or easy bound should be. That follows from the convexity principle of Fragmin and Lindelof. And by a subconvex bound, we mean a bound that is significantly better than the convexity bound. In the subnorm problem, it's not so clear what the trivial bound should be. So perhaps it's more appropriate to call such bounds baseline bounds, but with various heuristic techniques and general observations, we can set such baseline bounds for us, and then the task is to beat them. So by and large, both the convexity bound and these baseline bounds for the subnorm problem are those that you can address without much arithmetic. And then at a more technical level, the subnorm problem enters bounds for exponential sums associated with cusp forms, beloved objects of analytic number theorists, and various shifted convolution sums, say, associated with Hecke eigenvalues of the forms. And all these themes are interrelated. For example, improving subconvexity bounds you often find yourself in the need of subnorm bounds and bounds for exponential sums and bounds for shifted convolution sums. And vice versa, certain subconvexity bounds help us prove better subnorm bounds. So all these topics are interrelated. Okay, enough of motivation. So let me state the main result for us. Notation throughout the talk will be G stands for the group of unimodular complex matrices SL2C. K is a maximal compact subgroup of it, SU2C, so 2 by 2 unitary matrices, and gamma will be the discrete arithmetic subgroup SL2ZI, ZI being the ring of Gaussian integers. And the result that 5 years ago on the earlier Balu Fest I presented is a joint result that appeared in 2006 but was proved a couple of years earlier, jointly with Valentin Blomer, who is here, and Georgia Milicevic, who I don't know if he is here, but it's very early for him, but there is a chance that he's here as well. And it says the following. So take an L2 normalized spherical Hecke eigenform on gamma left divided by gamma and right divided by K. Now G divided by K on the right is isomorphic to the hyperbolic space. So in effect, we are looking at, in this theorem, Hecke eigenforms on hyperbolic 3 space. And spherical stands for the fact that when thought as functions on the group G, they are right K invariant. And let lambda denote the Laplacian eigenvalue of phi. Well, here in this theorem, we don't need the notation nu, but already I'm indicating how it relates to the Laplace eigenvalue so that you get used to this notation. Nu is a purely imaginary number in this situation. And then for every epsilon, the global subnorm of phi is bounded by lambda to the 5 over 12 plus epsilon. So here the baseline bound is lambda to the 1/2, and that has been improved to 5 over 12. Later, I will say a few words about, in general, at least in one, heuristics where the baseline bound might come from. But more importantly, let me emphasize that this result is the analog of the very famous, very celebrated result of Ivanets and Sarnak from '95, which proved the same kind of bound for SL2R and SL2Z. In that case, lambda to the 5 over 24 is what they achieved, and this result hasn't been improved since. So 5 over 24 and 5 over 12 here are very, how to say, very precise for the method we had. Very significant new ideas will be needed to improve those exponents. And I don't display in this talk, but let me mention that this result with my co-authors, Valentin, Georgia, and Peter Maga, we extended this result to more general number fields. And there we see that at real places, for the corresponding Laplacian eigenvalues, we get exponent 5 over 24, and at the complex places, complex embeddings up to conjugation of the number field, we get 5 over 12. So this theorem is a special case of a more general theorem. And also there are results by us and others, most notably by Abhishek Saha and Edgar Assing, that address the level aspect of the problem. But here, so where gamma is a more general congruent subgroup, but those aspects I will not talk about today. And then the main result for today is this very fresh theorem. So let L be a positive integer. So L will stand for which K type we are talking about. So already now let me remind you that irreducible unitary representations of SU2C have finite dimension 2L plus 1, where L is a half integer. And in this problem, in this theorem, the L's that come up are non-negative integers, and I exclude L equals 0 for simplicity. So L equals 0 is the spherical case, the K invariant case, and then the dimensions of the relevant SU2C representations are what positive integers like 3, 5, etc. I excluded L equals 0 from this discussion in that theorem, so that at the last line, where you see the bound that we obtained, the bound makes sense. For L equals 0, that bound would obviously be false. Anyway, so L is a positive integer for convenience. I is say a bounded interval, a compact subset of the imaginary axis. This will contain the spectral parameters nu for the forms participating in this theorem. Omega is a compact subset of G. That's where we restrict the soup norm. And then we take a non-spherical L2 normalized Hecke eigenform for G mod gamma with the following conditions. So I already told you that nu lies in I. So we talk about bounded spectral parameter here. Spectral parameter is not really moving. What is moving is the K type. So what do I mean? This cusp form phi generates a cuspidal automorphic representation that you can decompose. So when you restrict this representation to K, and you can decompose into various irreducible representations of K, each representation that occurs has multiplicity 1, and they form a consecutive sequence of representations starting with some minimal one that we call tau L. So there is a minimal dimension of a K type that occurs in the automorphic representation of dimension 2L plus 1, and then also dimension 2L plus 3, 2L plus 5, all those occur. And the minimal K type that you can also call minimal weight, although my co-authors don't like this word, we assume is tau L. So L stands for the minimal weight, so to say, or L. Minimal dimension is 2L plus 1 of the occurring K types. And we assume that phi is of minimal weight in the sense that it lies in this K type, so the K translates of phi generate this K type. And then, in fact, in this minimal K type, you can consider some natural basis, and we assume that phi is a basis vector in such a natural basis, which practically means that phi is an eigenfunction of the diagonal matrices contained in K. And then this diagonal subgroup of K acts by a character on phi. Okay, so in short, we tried to consider a very natural kind of Archimedean nu form in a non-spherical cuspidal automorphic representation. And then on the next line, I would like to convince you that the baseline bound should be L for the soup norm, restricted soup norm. So when the points are restricted to omega, and that we are able to beat or improve to L to the 26 over 27 plus epsilon. By the way, if you have any question, just speak up. Okay, so in the next, okay, there is a slide about other results in the weight aspect, but I should emphasize that apart from the last one, Ramaker, Wakatsuki, the results are not really comparable to our result because it addresses a rather different situation, but from a representation theoretic point of view, the situation is similar. They talk about, so the first 4 references talk about holomorphic Hecke cusp forms on the upper half plane in the weight aspect. So Shia in 2006 for weight K cusp forms could prove an optimal upper bound k to the 1/4 plus epsilon in the weight aspect. So you can call it somewhat analogous to what we are doing, but certainly we are not finding any optimal exponent. And in fact, for the restricted version of the Supnon problem here, the optimal exponent is not known either. So Shoumo, Das, and Jyoti Sengupta considered the case of, so Shia's result was for the group SL2Z. And Shoumo, Das, and Jyoti Sengupta considered compact quotients of the upper half plane coming from quaternion algebras, and there they could prove a power-saving upper bound for the Supnon in 2015. Steiner in 2017 considered half-integral weight cusp forms, and then Kayutin Steiner could prove the analog of Shia's result, and much more with a fresh new method in 2020. And the only result that's directly comparable with ours is Ramacher-Wakatsuki's very general theorem from 2020. It works for all kinds of semi-simple algebraic groups. But when you specialize their result to our situation, which is rather special, I must say, their result doesn't even achieve what we consider the baseline bound. So in the notation of this slide, they prove, now for this situation, they prove, although let me emphasize, their theorem is much more general, they prove lambda to the 5/12 minus some positive delta, and that's very far from what we consider the baseline bound, that is L. Okay, so what is this baseline bound business about? So let me here generate a very heuristic upper bound based on the pre-trace formula and its integrated version, which is the trace formula. So just very quick, let f be a compactly supported test function on the group G. And then this function gives rise to an operator. So originally the group G acts on the right on the L2 space G mod gamma, but this action of the group extends to an action of the convolution algebra, that is CCG, and this action is given as written in the formula. And what's important here, that this integral operator has a natural kernel that is given in the parentheses here. This kernel function, this automorphic kernel, is a sum that you can build out of f and gamma. So that runs to gamma. And now for this heuristic reasoning, we assume that RF is a positive operator that acts by eigenvalues that I denote by f hat phi. It's not automatic that these eigenvalues exist, but let's assume we are in a situation where these eigenvalues exist and then they are non-negative. And phi runs through an orthonormal system of to normalize eigenforms. And so in the pre-trace formula, the pre-trace formula means that we expand this automorphic kernel spectrally, and then we evaluate it at the diagonal. So we put G equals H. So this is a technology that was pioneered by Zellberg. So he considered the spectral decomposition. Right-hand side is the kernel at G equals H, and it has the indicated kind of spectral decomposition in the situation at hand. Plus there is a continuous contribution that I suppress for simplicity. And then when you integrate both sides, then you get the trace formula. On the right-hand side, the integrals become orbital integrals, and the left-hand side, the absolute phi g squares integrate to 1. And now let's assume for this heuristic that the spectral weights kind of pick a family of eigenforms script f. So think of these weights as being the indicator function of a family, although that is very hard to achieve. But let's assume we are in this situation, and let's assume that the identity element dominates on the right-hand side, even after integrating over G mod gamma. So both in the pre-trace formula and in its integrated version, we think of the right-hand side as being F1 practically. Now, when you integrate F1 on the right-hand side over G mod gamma, then of course you get the volume of G mod gamma, and then you, on the left-hand side, you get a weighted count of these cast forms plus also continuous integral weighted count for cast forms phi. So in effect, you would count the size of the family. This is how the Weil law is proved in practice. But of course, the details are more complicated because here I'm creating a situation that doesn't really exist. Anyways, we can, for a heuristic reasoning, we can think of all these conditions being satisfied, and then we get, with a quotation mark, that the sum of phi g absolute square of the family, so that's the original left-hand side in the pre-trace formula, that's like f of the identity element. Note that for gamma being the identity element, the corresponding f value is just f at the identity element. And then from the integrated version, we expect that that's like the size of the family of the volume. So this heuristic reasoning would tell us that on the left-hand side, each term by non-negativity should be bounded by the right-hand side. So about square root of the size of the family over the square root of the volume should be a reasonable pointwise upper bound for phi g. And then the question is how small we can make the family. Anyways, this is what I call the baseline bound. And in our situation, we look at Cuspidor representations with K-type, minimal K-type tau L and bounded eigenvalue. And then on later slides, you will see, and you probably already know, that the Plancherel density runs for such Cuspidor representations is around L squared. And then we want to pick from each, we want to emphasize a single form in the K-type. So our wishful thinking is that the size of the family should be L squared. That's what how many cusp forms we grab at the same time. And then the square root of this L squared is L. So this is my explanation of the baseline bound L for that situation. And then we can be proud if we beat that baseline bound. So the exponent 1 should be decreased. And that's what we do. Now, one very, very interesting aspect of this project and very educational for us is that for this project, at least if you want to understand what's going on, you need to know about the generalized principal series of SL2C. So non-unitary representations of SL2C enter the picture. That's very astonishing because in all these problems, we usually don't need to see any further than unitary representation. So here I briefly summarize a convenient description of the generalized principal series of G, which is SL2C. These not necessarily unitary representations are indexed by the complex number and the half integer, nu and p. And then the space for the representation can be described. And this is, apart from our notation, is basically taken from a very nice book by Gelfand, Grayev, and Vilenkin, Generalized Functions, Volume 5 from 1966. And they say, let's take V nu P be the space of functions in two complex variables that are infinitely times differentiable with respect to both variables and their conjugates, at least away from the origin, and satisfy a homogeneity condition as displayed. And then we can put a topology on this space of functions by locally uniform convergence away from the origin together with all their, and the same for derivatives. So this makes the space into a Frechet space, which is not too far from being a Banach space or a Hilbert space. And then, so you don't need to really remember any of this, just note that there is a natural space, topological vector space, on which the group SL2C acts in a very natural fashion. So this action should be very, very familiar to anyone who worked on quadratic forms, where usually SL2R or SL2Z is acts on the two variables, but here the two variables are complex. So this is the definition of the representation pi nu p, and then it turns out that this space admits an invariant Hermitian inner product if and only if either nu is a purely imaginary number, and that we call, so those representations constitute the true principal series, and together these representations form the so-called tempered unitary dual. But there are also some exceptional cases where the representation is unitary. In those cases, p is 0 and nu is between -1 and 1, and not 0 because that has already been put into the principal series. So those form the complementary series. So the principal series and the complementary series, so the cases in the two bubble points, form the unitary dual of SL2C, but we shall need the non-unitary cases as well. And now once you have a Hermitian inner product on your space, you can complete it into Hilbert space, and then you have a continuous Hilbert space representation. Now, we can refine this picture by decomposing the space into finite dimensional subspaces according to the action of the maximal compact. And those finite dimensional pieces can be further decomposed into one-dimensional subspaces according to the action of the circle group. That's why I call it, namely diagonal matrices inside the maximal compact. So here is how this decomposition looks like. So if the second parameter of the representation is P, then the K types that occur in the representation they correspond to L, at least absolute value of P. So once again, the Lth K type has dimension 2L plus 1, but L is not necessarily an integer. It can be any half integer that's congruent to P mod 1. But in our situation, so the representations that occur in the automorphic L2 space, L2 G mod gamma, all these parameters will be actual integers, not half integers. And then for an L piece, which is a finite dimensional piece of this representation, it has dimension 2L plus 1, and you can find the natural basis according to the various characters of this subgroup, and those characters. So they are of the characters that enter here are of the form e to the 2qi rho. So you raise this parameter to 2q, and q must run from minus L to L, and there are 2L plus 1 such integers or half integers. And then they really define these one-dimensional pieces for us. And so in our original problem, we are interested in a phi that spans this very one-dimensional piece. That's what we are interested in. And now something very interesting happens when you ask yourself how these representations are, these generalized principal series representations are irreducible. So it turns out when nu is not a half integer, then the representation is irreducible and isomorphic to the one you get by flipping the pair nu p to its negative. And if nu is a half integer, that the conclusion still holds true when absolute value of nu is at most absolute value of p. And then there is some very interesting exceptional case that is relevant for us. That's what I'm telling you about. If nu is half an integer and absolute value nu exceeds absolute value of p, then they are both reducible. That's already very interesting. Now, without loss of generality by symmetry, you can assume that nu is positive. Then in V nu PL, the k types that correspond to L less than nu, and then also necessarily at least absolute value of p. So these finitely many k types together form, they span a closed invariant subspace. It's finite dimensional actually invariant subspace of V nu p. And when you take the corresponding quotient, that's irreducible. On the other hand, for V minus nu PL, the other guy that we need to examine here, the k types with L at least nu form a closed invariant subspace, and that's infinite dimensional, and that the restricted or induced representation on that invariant subspace is irreducible. So in one case by a quotient, in another case by passing the subspace, we get an irreducible representation. And both of these turn out to be isomorphic. Both of these turn out to be irreducible and isomorphic to p nu and p minus p nu. So look what is happening here. We started with parameter nu p and minus nu p, and after a small surgery that we make on the spaces, we end up with representations isomorphic to p nu and p minus p nu. So there is an almost symmetry when you flip nu p to p nu. The two representations are very close to each other. More precisely, if you look at this decomposition and you take the space of endomorphisms, just vector space endomorphism of the space on the left-hand side. So take endomorphisms, ring of V nu p, then because of this decomposition, that endomorphism ring comes with a block matrix decomposition consisting of blocks hom of V nu p m and V nu p n. And when you restrict this block decomposition, when you only look at blocks with indices at least absolute value of p and also absolute value nu, then in the representation for nu p and p nu and also minus p nu and minus nu p, so in all these four representations, the group will act in the same way in those spaces, in those block matrices. And this will have a dramatic effect for our problem. Now, I still need to build up some theory for this project. There is the wonderful seminal work of Gelfand and Naimark, two very, very substantial papers from 1947 and 1950, which generalize the phenomenon that, so from finite group theory, you know that the group algebra CG is isomorphic to direct sum of full matrix algebras. So this theorem can be generalized to this infinite group, Lie group G equals SL2C. Namely, they showed that there exists a Hilbert space isomorphism. L2G is isomorphic to essentially an integral over the tempered unitary dual of G. So here I spelled it out in very concrete form. I made the integral and sum on the right-hand side so that ITP pairs exhaust the principal series. And apart from t equals 0, where 0p and 0 minus p are equivalent representations, each representation occurs with multiplicity 1. And for t equals 0, the measure is 0, so that is it's like those doublings were not even there. So the L2 space of G decomposes to these full infinite dimensional matrix algebras, endomorphisms of VITP, with respect to measure that is proportional to t squared plus p squared times the Lebesgue measure for t. And you can, the actual constant of in front of this density is depends on the core measure you use on the group G. And so we can just pick a Hor measure where t squared plus p squared dt is the Plancherel measure. And what's amazing that if you look at a function on the left-hand side, say initially compactly supported smooth functions, then the corresponding operators in these various endomorphism pieces are fully independent. And there is a Plancherel theorem which says, well, not fully independent, but there is of course an obstruction. The Plancherel theorem, these for each piece in the corresponding endomorphism ring that I call pi f here, the relevant norm for the Hilbert subspace is the Hilbert-Schmidt norm. And so on the left-hand side, so there is a Pythagorean theorem which says that the L2 norm of f squared is the integral of the various Hilbert-Schmidt norm squares that come from pi f when you integrate against the Plancherel measure. But apart from this joint square integrability, you can choose, as long as you are happy with a function in the L2 space, you can choose any action of your function in the various pieces. And here I emphasize compactly supported smooth functions on G because they form a dense subset of the Hilbert space on the left. And for such test functions F, the corresponding operators, so the things you see inside these endomorphism pieces are trace class operators. And there is an inversion formula. You can reconstruct Fg from these pieces by taking the traces like here and integrate against the Plancherel measure. So here there is really a transform given by pi f and an inverse transform, and you can extend these transforms to the full L2 space, and then you get an isomorphism. In particular, there is surge activity here, which is very important. Now, I'd like to introduce, starting from this picture, the generalized spherical transform. So for a fixed L, as in our theorem, we'll be interested in test functions f, which have the following property. So the corresponding piece on the right-hand side should act by a scalar on the Lth k-type component and by 0 on the other k-type component. So remember, we had this decomposition. This is an orthogonal decomposition of the space. And we want to see a scalar action on the Lth component and the 0 action on the other components. And one can identify easily what these functions correspond to on the left-hand side. They form a Hilbert subspace defined by these two conditions. So the function should be k-central, so it commutes with the action of k. And also, if you look at 2L plus 1 times the character of tau L, so that convolution by the conjugate, convolution over k by the conjugate of that character corresponds to projection on the Lth k-type. F should be invariant with respect to left and right convolution. So this is the function theoretic description on the left-hand side of what we want on the right-hand side. So instead of general actions in the various endomorphism pieces, I want some very simple actions. So in effect, I want our pi f to favor the Lth piece and Lth k-type and forget about all the K types, and I want a very simple scalar action. And then this scalar can be actually calculated. We talk about a scalar action on a space of dimension 2l+1. So then the scalar can be identified, of course, as the trace divided by 2l+1. I mean, if you act by a scalar on a space of dimension 2l+1, then the trace is 2l+1 times that scalar. And the trace itself can be calculated just by plugging in as an integral of fg times what we call the spherical trace function. So the spherical trace function is defined from the group action in a straightforward way like this. Although this definition is a bit abstract, and later we'll have to see more concrete descriptions. And then the previous inversion formula that I indicated here gives rise to an inversion formula here as well. So we have this spherical transform that is the trace, and you integrate with respect to the Plancherel measure the spherical trace function, you get back fg. So that's a special case of this very general Gelfand-Neumar theorem. And again, we have surjectivity, and there is a Plancherel formula. So you can easily calculate the Hilbert-Schmidt norm of these scalar acting transformations. Well, what is it? So 2l+1 times the sum of squares and the diagonals. So that would be 1/2l+1 times the absolute square of that. You integrate with respect to the Plancherel measure. That's the L2 norm square on the left-hand side. So again, there is a surjectivity phenomenon, and this L2 condition is the only obstruction, as long as you are happy with L2 function satisfying this conclusion. But then later in practice, you want to take rapidly decaying test functions f, and then it's not so straightforward to see what kind of transforms those have. Now, the spherical trace function was defined in the abstract, but it has a very concrete integral representation. At G, you have to integrate over K, kappa L, K inverse GK, where kappa L is given by this very simple-minded function from the matrix entries of the matrix. But note that kappa L, so this simple-minded expression has to be applied not on G, but K inverse GK, and then you integrate over K, and then things become complicated. It turns out that this function extends holomorphically in the new variable, and it also satisfies a soft general bond that we skip here. And then it turns out that the spherical trace function has some remarkable symmetries. So there is symmetry with respect to G, and there is also symmetry with respect to the parameters of the representation. So this right-hand side formula follows right away from the definition. The left-hand side saying that it is real valued is more accidental, reflecting that basically that in the Cartan decomposition, the middle piece, which is a diagonal matrix, or 1/(1) entry determines the other because of the determinant 1 condition. That's vaguely, well, the actual proof is deeper than that. But for usual spherical function, that's actually a proof. But what's really remarkable, and you can find, and the source of that is that I already explained to you. It is really an application of that when you flip nu and p when you can, so that nu and p are congruent to mod 1, so nu is also a half integer, then you get the same spherical trace function, as long as L is sufficiently large, larger than either of the two parameters. So that's very amazing and shocking, as you will see in a moment. Because then by the previous two slides, if the function f decays rapidly, then if we scroll back, the spherical transform was cooked up from the spherical trace functions with this fg. Then all these symmetries possessed by the spherical trace function in the new p parameters will be inherited by the spherical transform. So it says that on the one hand, the spherical this generalized spherical transform f hat extends holomorphically in the new variable, and it satisfies this symmetry. And that means that nu and p are not independent as we thought. So, for example, we want to emphasize p equals L and neglect p less than L. But that means that if you plug in, say, L for nu, then we want to neglect f hat LP, but that means we also have to neglect f hat PL. So at the Lth piece, we create many zeros, and that causes all sorts of troubles. I think this all too fast, but you can review the slides. I will put them on my webpage, or you can review the video. But this really causes a problem for us when we try to select the Lth piece, Lth K type from our representations and not the other types. And as I told you already that we want a rapidly decaying test function, and ideally we would like to use a compactly supported test function, for which case Wang in 1974 characterized the possible transforms f hat that these f's correspond to. So this is an analog of the Pelley-Wiener theorem, and it says that in this HTL space, f is smooth and compactly supported if and only if this transform not only extends holomorphically and satisfies these symmetries, but also has rapid decay in vertical strips. And then it's a very precise upper bound, which depends on the support of the function. And we found this theorem too restrictive for our purposes. Namely, we couldn't quite find the test function that satisfies both star and this very strong upper bound for the transform. Namely, this exponential was too small for us. So in other words, we couldn't really make our test function compactly supported. And so we generalized Wang's theorem to what we can call the Schwartz class subspace of HTL. So if you are happy with going not with compactly supported functions, but with functions of rapid decay along with their derivatives, then we don't need the transform to be that precisely decaying in vertical strips. It is just sufficient that it decays with some implied constant rapidly in vertical strips. And so this generalization of Wang's Pelley-Wiener theorem was very useful for us. So in the end, we settled for with the following test functions, in HTL. We define the function in terms of its transform. So we prescribe on the spectral side the weights in advance, and we settled for these Gaussian weights. So this transform function satisfies all the conditions. So item 2 in this theorem and also star. So on the function side, f is smooth and rapidly decaying with derivatives. And this does provide a positive operator RF on the automorphic L2 space, which puts about 1 over L weight on the V nu LL component with bounded nu and a negligible weight on all the other components V nu PM. So note that when M is distinct from L, already we put weight 0 because that's how we created this function space. So for M not equal to L, that is already out of the game. And if P is not equal to L, then P is strictly less than L, which makes this function exponentially small. That's what I mean by negligible. So at this point, we found a spectral weight function with rapidly decaying test function, which emphasizes the Lth K type for those representations where L is the minimal K type. And then when we pass from F to its Fourier coefficient, so when we average F we integrate over the circle group against the character, and this Q should be chosen in the same way as our original cusp form in our original theorem, which was here. So here I said phi is an eigenfunction of the matrices, so that selects a character of the circle group, and the same character has to be used for this averaging process. Then when we pass from F to these Fourier coefficients, then we still get the positive operator, which now puts about 1 over L weight on the one-dimensional components V nu L L Q with bonded nu that occur within the automorphic L2 space, and a negligible weight on all the other one-dimensional species. So at this point, in 3 steps, we are down to emphasizing one-dimensional species in cuspidal automorphic representations occurring in L2 G mod gamma. First, we went down to P equals L, then we went on to M equals L, and then we went down to R equals Q. So in 3 steps, we are now seeing in the spectral, on the spectral size, this single one-dimensional spaces, one of which contains phi. And I only have a few minutes left. I planned for a 60-minute talk. But the upshot is that F itself from the inversion formula, sorry, I'm trying to find, F can be expressed by the inversion formula for the prescribed spectral weights and the spherical trace function. And then now we average F over, so we take its Fourier coefficient, Q Fourier coefficient over the circle subgroup. So in effect, that's the same as taking the Q Fourier coefficient of the spherical trace function. So at this point, things get really difficult from an analytic point of view, because already the spherical trace function was a difficult analytic object. And now we find ourselves in the need of taking its Q Fourier coefficient. So the already complicated object is integrated like this, and we have to analyze, we have to estimate this Fourier coefficient, Q Fourier coefficient of the spherical trace function. Namely, by using a standard amplifier, we can finally bound our cusp form squared at G by such an expression, where by amplification now gamma doesn't run through SL2Z, but all sorts of 2x2 matrices with Gaussian entries. And for such a gamma, we can scale down gamma to gamma tilde so that it lies in SL2C. And then there are certain weights coming from amplification. And then we conjugate gamma with G as in the pre-trace formula. And the upshot is that we need to understand the sup norm for all these conjugated gammas when scaled down by that determinant, square root of determinant. And we have good control over the weights coming from amplification. So X1, capital L is the amplifier length. It's a parameter at our disposal. X1 is bounded by capital N. Xn is supported on product of 2 special split Gaussian primes or their squares, and there Xn is at most 1 and Xn is 0 otherwise. So we have a very concrete upper bound for phi G, pointwise upper bound in terms of this averaged spherical trace function. And this leads us to analyzing the Q Fourier coefficient of the averaged spherical trace function. And let me tell you that this is a rather difficult task. So we found that the best way to analyze it is to put G into Cartan form. So we represent G as K1 from the maximal compact times diagonal of R and 1 over R matrix, and then a K2 from the maximal compact. So that already introduces us 7 variables. Because the maximal compact we parameterize by 3 Euler angles. And then when you look at the definition of the spherical trace function, that involves an integration over SU2C. That brings in another 3 variables for integration. So we have to jiggle with these 10 variables. And so that's a bit scary first. But then by rather straightforward manipulations, we end up with an expression which after the triangle inequality gives the following upper bound for the every spherical trace function. It's something very concrete where A, B, C, D abbreviates certain functions which are of absolute value at most 1, and in fact A squared plus B squared equals C squared plus D squared equals 1. And then from Young's inequality, very carefully examined and Stirling's formula, we already see that the integrand inside is over 1 over something. But of course, depending on Q, this something can be as large as 1. And in the best case, it is 1 over square root L, which is still very far from sufficient for us. Essentially, we want an upper bound of 1. And then we examine when we can improve these bounds. And we find that the contribution of very small t or very large t is negligible, because then this factor is very small. If t is not too small and not too large, so that this denominator here is sizable, not too close to 0, then because of the nth power, negative nth power, the contribution of the second factor is negligible unless r is very close to 1, or is the middle Cartan coordinate. And then we analyze this inner integral, and we see that unless phi and t are in a very special constellation, this integral is very small, and this forces G to be close to diagonal. So in the end, we get this very clean, but it involves hard work, upper bound for the averaged spherical trace function. So we have essentially a bound 1 always, and when G is somewhat away from the maximal compact or somewhat away from diagonal matrices, then we have better upper bounds. And then we got to the end game, and maybe I have 1 minute left. So we estimate carefully, going back to amplification here, we estimate carefully, oh, Valentin, hi. And we estimate carefully the number of matrices whose determinant is of a given type, either 1 or product of 2 Gaussian primes or their squares, and we control how far the corresponding conjugated version of gamma is away from K and D. And in the end, we get a bound for phi G like this. Here we have dyadic ranges for the 2 kinds of distances, and we can, it's not hard, upper bound at this point, the dyadic sum by L inverse 1 over L, the amplifier length, and L square L to the minus 2 over 9. And so we win. The optimal choice is L to the 2 over 27, and that yields our final estimate. And sorry, I had to rush through a little bit at the end, but my last slide is identical to the last slide of my previous talk 5 years ago. Happy birthday, Balu! Many more beautiful theorems and years to come. Thank you for your attention.
Thank you for the talk. So we still probably have time for one quick question. If anybody has a question, please unmute and ask. Okay, if there are no questions, then we thank the speaker.
Thank you so much for having me. Thank you. Wonderful conference. Thank you so much.
So we can just switch over to the next speaker.
Hi.
Yeah,
should I share my screen?
Yeah, you should share. Yes, sure.
Is it visible?
Yes, it is. Yeah, it's perfect. Full screen. Oh, you can. You know, it's not. You can make it full screen. Yeah, it is the.
Yeah. Okay.
Yeah, that's. So next speaker is Anup Dikshit, my colleague from IMSC, and he would be speaking on general Dirichlet series with positive integer coefficients. Please, Anup.
Yeah. Thank you very much. I would like to thank the organizers for putting together this nice big conference. In the honor of Professor Balu. Professor Balasubramaniam has played a significant role in my mathematical journey so far. Not only was he one of my first teachers in number theory, but also he played a role in me choosing to pursue a career in mathematics. In fact, choosing to do my undergraduation in mathematics because I had the opportunity to attend one of his lectures as a high school student in Mumbai, HVCSE Mumbai. So it's an honor to, I'm very, very grateful to the organizers for giving me this chance to speak on the 70th birthday of Professor Balasubramaniam. Very happy birthday to him. And hopefully for his 75th birthday, we will have a much grander in-person conference with samosas and coffee and chai, etc. Okay, so with that note, I'm going to talk about general Dirichlet series with positive integer coefficients. So let's get to what Dirichlet series is. So we all know that a standard Dirichlet series is a series of this form, summation n going from 1 to infinity, a n over n to the s. And such a series is convergent on only a half plane, real part of s greater than some sigma. And a general Dirichlet series is a series of this form, summation of n going from 1 to infinity, a n over lambda into the s, where lambda 1, lambda 2 is some increasing positive real numbers, strictly increasing positive real numbers. And this type of series is also convergent only on a half plane, which is, let's say, some real part of s greater than sigma. In fact, general Dirichlet series have many properties similar to that of standard Dirichlet series and many properties quite different, many properties that do not enjoy which we have for standard Dirichlet series. And a good, one of the good reference for this would be a nice book by Hardy and Reeves on general Dirichlet series. Okay, but otherwise, the study of general Dirichlet series has received scant attention in the literature. So today I'm going to talk about how special these, in some aspects, how to pick some special functions out of this general Dirichlet series. Okay, so when we talk about Dirichlet series, the most standard example which takes the spotlight is the Riemann zeta function. Now the zeta function is defined as summation n going from 1 to infinity 1 over n to the s in the region real part of s greater than 1. And in this very region, it also has this Euler product over all primes 1 minus 1 over p to the s inverse. And this is due to the unique factorization of natural numbers into primes. It is absolutely, this series is absolutely convergent on real part of s greater than 1. And it has an analytic continuation. Okay, I see that there are some chat. If there are any questions, please let me know. It's okay to interrupt. Otherwise, I cannot really see the chats while I'm speaking. So the zeta function has an analytic continuation to the whole complex plane, except for a simple pole at s is equals to 1 with residue 1. And it also enjoys this symmetry given by the functional equation. If I define psi of s as gamma of s over 2 times pi to the minus s over 2, this gamma factor times zeta of s, then this resultant function psi of s has a symmetry around the half line, which is psi of s is equals to psi of 1 minus s. Now, zeta function is a very special function. It captures many interesting properties about distribution of prime numbers. For instance, the prime number theorem is just the consequence of the fact that zeta doesn't vanish on one line, and it has a pole at s is equals to 1. Furthermore, because of the Euler product and the functional equation, because of the symmetry and the fact that it doesn't have any zeros to the right of 1, Riemann predicted that all the zeros of the zeta function, which lie in this critical strip when the real part is between 0 and 1, must lie on the half line. This is the famous Riemann hypothesis, which has many, many consequences and one of the most celebrated problems of today. So Riemann zeta function is going to play a central role in this talk as well. And just keep in mind that we will try to capture what makes Riemann zeta function so special. That's basically what's going on in the background. So in order to realize that, let's consider a function which is similar in definition to Riemann zeta function, namely the Hurwitz zeta function. Now, Hurwitz zeta function is defined by this particular series, summation n is equals to 0 to infinity 1 over n plus a to the s, where a is some value between which is greater than 0, less than equals to 1. This series is absolutely convergent for real part of s greater than 1. And it also has an analytic continuation to the whole complex plane, except for a simple pole at s is equals to 1 with residue 1. So it's very similar to the Riemann zeta function up till this point. However, it doesn't have, and remember that when a is equals to 1, this is just the zeta function. Beyond that, the similarity disappears. The functional equation is nowhere like the functional equation of the Riemann zeta function, but it still has a certain kind of functional equation. Zeta of 1 minus s alpha can be written as some gamma factor times this f of s alpha plus f of s minus alpha, where f of s alpha is given by the series. And we know that if a is not equals to 1 or half, which in both cases is like that, it resembles the Riemann zeta function, the Riemann hypothesis is no longer true. In fact, the Hurwitz zeta function has zeros, infinity many zeros, and real part of s greater than 1. Okay, so the question is what makes the Riemann zeta function special? Now, let's consider a more general type of dirichlet series. Let's say f of s is summation of n going from 1 to infinity, 1 over lambda n to the s. So this is a general Dirichlet series, and of course this lambda n's have this property that they are all strictly increasing set of positive positive real numbers. And suppose this series absolutely converges in the half plane real part of s greater than 1, let's say with analytic continuation to the whole complex plane, except for a simple pole at s is equals to 1 with residue 1. So let's consider the set of all these functions, and we would like to determine what makes the zeta function so special. How is zeta function different? So from an arithmetic point of view, you can say that zeta function has an Euler product, which is not true in general, of course, and therefore it captures properties about distribution of primes and so on. And also it enjoys the symmetry because of the Riemann's functional equation, which is also not true for other functions of this type. But what we are interested in is to give some pure analytic way of differentiating the zeta function, which would totally come from the growth. And this work was initiated, I would say, or this work is initiated by Burling, and that is what we are going to focus today. So let me first describe Burling's result. Now, Burling is Arne Burling is a Swedish mathematician. He's a very famous Swedish mathematician who is best known for having single-handedly deciphered some German cipher machine, which is considered to be much more complicated than Enigma, for which Alan Turing is given the credit. He's famous, and he could decipher it just using pen and paper in a matter of weeks. So he's like some stories to be inspired by. Okay, so this is a result, but unfortunately, Burling did not publish too many papers, and he wrote even less number of papers. He has less number of papers in number theory, and this is probably the only paper that he wrote on Riemann zeta function. Okay, so the main result is as follows. Exactly going by the question that we are asking, if we consider a general Dirichlet series of this type, can we identify the Riemann zeta function from from a purely analytic perspective? Okay, so let's consider a function which satisfies the following property. It looks like summation n going from 1 to infinity 1 over lambda n to the s, and it's absolutely convergent on real part of s greater than 1. Suppose it has an analytic continuation to the whole complex plane, except for a simple pole at s is equals to 1 with residue 1. And let's also assume that it vanishes on all negative even integers. Now these are anyway zeros for zeta function, and these are called the trivial zeros, which arise from the poles of the gamma function itself. So let's put in this condition as well for f. And additionally, let's say f satisfies this growth condition. Now this growth condition basically tells us that for r greater than 3/2, if I look at the circle of radius r, then your f of s is less than some gamma r divided by 2 pi to the r. However, if I replace this 2 pi with 2 pi plus epsilon, this is no longer true for all s. So this is really a strict form. And this property is also holds for the Riemann zeta function, as we will see very soon. This is implied by the functional equation. Now, if all these properties hold, then in fact the function is nothing but a zeta function, or zeta of s half, which is essentially the zeta function times this 2 to the s minus 1. So in other words, zeta function is uniquely determined by this growth condition as long as we have trivial zeros in place. Okay. So let me say a few more words about this this theorem. What if I replace this 2 pi with a certain interval? If I say that this growth condition is satisfied, where instead of 2 pi you vary this over a certain interval, then what happens? Now that it is also quite strange to note the following. Suppose my f satisfies this growth condition, that it's less than gamma r over 2 pi k to the r. So instead of 2 pi, let's say 2 pi k to the r, but doesn't hold for 2 pi k plus epsilon. Okay. Then in fact, if I take any k between half and 1, then there are no such functions f. So remember that for the Riemann zeta function, this k is just equals to 1. And between half and 1, there is no such function. But if we are less than half, and I take any subinterval of a subinterval of 0 to half in 0 to half, then there will be infinitely many function f with this k lying in the subinterval. So k lying in this interval C to D. So really speaking, zeta function is the function of minimal growth. Like if we forget this particular condition and just just say that okay, it satisfies this growth condition, then well, zeta function is really the function with minimal growth. Like as soon as we make this, if we and it is really lying as the boundary element of the collection of all these functions, which satisfy this type of a growth condition. Okay, so this was what was pointed out by Burling, and in his paper he also asks this question: how strong is this trivial zero condition? Can we drop this trivial zero condition? And that was answered by Freeman Dyson, the mathematical physicist who passed away last year just before the lockdown began. He in fact showed that the trivial zeros condition can be weakened, but we really do need to have some condition on how the function behaves on the negative integers. Okay, so that's this is the theorem of Burling. So our first goal would be to one of the goals of today's talk would be to generalize this theorem in a larger setting. And in order to do that, we first need to define these growth parameters, a growth condition. So let's say your f of s is given by this dirichlet series, an over lambda n to the s, and suppose it has analytic continuation with possible pole at s is equals to 1. Now we define this growth condition, which is given by, let me keep an eye on the time. Okay. Yeah. So the growth condition, which is given as on the circle of radius r, f of s is less than gamma r to the df divided by alpha f to the r. So this holds, but if I replace alpha f with alpha f plus epsilon, this condition no longer holds. Like as soon as I make the growth slightly, so this is really the optimal growth which is attained. So if this condition is satisfied, then we say growth condition dagger is satisfied, and we call df and alpha f as the we call df as the degree of the function and alpha f inverse as the conductor of the function f. So this is the growth condition that we introduce. And in this scenario, this is similar to that of the Burling's growth condition. And for an example, you can see that the degree of the zeta function and the degree is 1, and the conductor and alpha of zeta is 2 pi. So I should also mention that if I look at Hurwitz zeta function, they will also have the same degree and the conductor. Okay, let me just say one word about what happens in the case of Hurwitz zeta function. They are of course not included in this set because of this trivial zero condition. So in fact, all the Hurwitz zeta function can also be realized as the boundary element of some collection of functions, which would follow from the result of Dyson. Okay, so this is the growth condition that we have. But there is another natural way to define, or there is a natural way in the literature to define these parameters degree and conductor, and that is through the through the functional equation. Now I say that the function f satisfies a Riemann type functional equation if there exists real numbers, positive real numbers, q and alpha I, q strictly greater than 0, alpha I greater than equals to 0, and some complex numbers beta I with a real part of beta I greater than 0, and some omega with which is a root of unity, such that if I multiply this particular gamma factor to f of s, and the resultant function phi of s would satisfy this symmetry. Phi of s is equals to omega times phi bar of 1 minus s1. So if this is satisfied, so this is similar, this is a very similar looking function as the functional equation of the Riemann zeta function. Then we say that the function satisfies if the Riemann type functional equation. And if it does so, then there is a way to define degree and conductor. As we saw in one of the previous talks today, the degree is defined as twice of summation of all these alpha i's. This is a finite product. I should have written I is equals to 1 plus m or something. And this qf is the conductor is defined as the following thing: 2 pi to the df q square product of I alpha I to the 2 alpha I. Now these definitions of degree and conductor bear a similarity to the definition of degree and conductor that we have incorporated using our growth condition. So the degree coming from the functional equation would be equal to the degree coming from the growth condition. And the conductor, remember I defined alpha inverse as the conductor, and that is very similar to the conductor defined as qf, which is just differs by 2 pi to the df. Okay. So now we have a notion of degree and conductor just coming from the growth. Now remember that whenever we have a functional equation, we automatically have a growth condition. But growth condition as such is a much much-weaker condition. There will be many functions which may or may not satisfy the functional equation, but would satisfy the growth condition. These definitions would are more general than that of the that in the case when we have a functional equation. So one of the ways to look at Burling's result is as a converse theorem. Now, just to highlight it, let me remind you of Hamburger's converse theorem. So he says that it says the following: if you have a Dirichlet series from a summation of n over n to the s, absolutely convergent on real part of s greater than 1, which has an analytic continuation except for a possible pole at s is equals to 1, and suppose it satisfies the same functional equation as the Riemann zeta function, then it has to essentially be the Riemann zeta function itself, constant times the Riemann zeta function, where the constant is a complex number. Now, one should look at Burling's theorem in the following perspective. We don't really need the full strength of the functional equation All we need is the growth has to be very similar. That means it has the same degree and the conductor. And we also need that, and we also need the trivial zero condition, which again comes from the functional equation. So this is like a subset of conditions that we can extract from the functional equation itself, and that itself determines the zeta, uniquely determines the zeta function amongst some the category of functions which are given by summation 1 over lambda into the s. So that's in a way it's a converse theorem as well. We're given a degree and a conductor and some constant, we extract the Riemann zeta function. Now there are other converse theorems for L functions associated to modular forms and so on, which are Hicker's converse theorem and Wei's converse theorem, but we are not going to focus on that. I just thought of mentioning. Okay, so now in order to talk about, in order to state my main result, let me introduce this class B, which I will call the Burling class. Now, Burling class consists of all those meromorphic functions that satisfy the following properties. So it has it has the general Dirichlet series representation, summation n going from 1 to infinity n over lambda n to the s. Lambda n's look exactly like we had before, and I would also force my n's to be positive integers. And suppose this general Dirichlet series is absolutely convergent in the half-plane real part of S greater than 1. And let's say it has an analytic continuation to the whole complex plane, except for a simple pole at S is equals to 1 with residue rho f. Now we will certainly have a pole because of Landau's theorem. Now Landau's theorem also holds in the context of general Dirichlet series. As long as we have positive coefficients, we will have a pole on the axis of absolute convergence. S is equals to the axis of absolute convergence. But this need for the simple pole is actually not there. But our main theorems that I have shown are when we have a simple pole. So just for simplicity, one can probably work out the details when we have a pole of a higher order. Okay. So it has an analytic continuation with a simple pole with at S equals to 1 with residue rho f. And suppose it satisfies the growth condition dagger, that's the gamma of r to the degree divided by the conductor to the r. And let's say the invariants, it satisfies the growth condition and therefore gives, there are these invariants df and alpha f associated to it. And let's also force the trivial zero condition that on all the negative even integer multiples of the degree, the function takes value 0. Then, in fact, one can one can get a theorem very similar to that of the result of Burling. So it says that if you have a function in B with, let's say, the degree as a positive integer, and suppose it satisfies this condition, alpha f is greater than something pi times rho f divided by sine pi over 2 df equal to the df, some weird looking condition. Then, in fact, there are at most twice of df number of elements in B, such that their degree, their conductor, and their residue are the same. So this is a strict generalization of Burling's result. Now, where if you take the degree to be 1 and the conductor to be 2 pi, then this will precisely yield Burling's result. Then this condition and the residue to be 1, this condition will be satisfied and it will yield Burling's result. So this is what I showed, which appeared in last year, and there is a recent improvement that we can drop this condition, and then we will still get some finite number of elements in the Burling class with the same degree, conductor, and the residue. I will talk more about what happens when we drop the condition, what sort of consequences we get in a short while. Okay. Now, to give some context to this theorem, let me talk a little bit about a more well-known class which has been extensively studied, namely the Selberg class. Selberg class of L functions was introduced by Selberg in 1989, and it consists of all the functions which satisfies the following conditions. It has a Dirichlet series leading coefficient 1, absolutely convergent on real part of S greater than 1, has an analytic continuation with a possible pole at S is equals to 1. This is an Euler product, Euler product given by f of s is product of fp of s, where log of fp of s is just the summation of bp to the k over p to the ks, and bp to the k satisfy this upper bound. And it has the functional equation, exactly the Riemann type functional equation. And there is a condition, which is the Ramanujan hypothesis, which is a condition on the dirichlet coefficients. So they should not grow faster than any polynomial. Okay. So this is the Selberg class, which is expected to capture all the interesting L functions arising from automorphic forms. And there are several conjectures on the Selberg class. One of the conjectures which was explained in the first talk today is that the degree and the conductor are non-negative integers. We know very little about it. What we know is that the degree cannot take values between 0 and 1. So this is due to Richard, Bochner, and Conley and Ghosh all independently, achieved all independently. And the best that we know is due to the work of Perelli and Kagzarowski about 10 years ago. And it says that degree cannot take values between 1 and 2. But now one may ask, can we classify elements with a given degree? And to answer that, we only know the classification of elements in the Selberg class for degree is equals to 1. And that is precisely given by the zeta function and the Dirichlet L functions and shifts of Dirichlet L functions, where chi is a non-principal primitive character and theta is some real number. Okay. But there is another conjecture. Okay, so let me just say that the classification of elements of higher degrees is not known. So there is another conjecture. In order to introduce that, let me introduce this relation. We said F is related to G, F and G being elements in the Selberg class, if F is just a vertical shift of G. And let's call S D as all the elements in the Selberg class with degree equals to D. Then there is a conjecture which is called the countability conjecture. It says that for any degree up to this relation, the total number of elements is countable. So for degree, for D is equals to 1, of course, we have Riemann zeta function and Dirichlet function countable. The rest are the vertical shifts of Dirichlet functions. Yeah, so for higher degrees, this is still a conjecture, and we don't know this for any other function. But if you go back to our result, it basically tells, I mean, it doesn't really tell us much, but it does tell us that if you fix a degree and you give a conductor, actually this, the way I've stated, it's not the best way. We actually have something stronger. You don't need to assume that this alpha f is equals to alpha g. You can assume that alpha g lies in a neighborhood of alpha f. That would also give us the result. Just like in the case of Riemann zeta function, even if that we had that around, even if we had that the conductor takes value, like even if we had the alpha f takes value from 2 pi minus 2 pi of k, where k is between half and 1, still the unique function is a zeta function. Very similar to that, we can replace this with an interval, and once we have an interval, we have countably many elements. However, the thing which kills us is the residue. Of course, that we don't know how to fix, but again, a similar looking result, which kind of not similar, but something which seems related to this countability conjecture. Okay, so this is just to give some idea about what we are trying to do. So what one of the first corollaries that we will have is given degree, conductor, and a residue in the extended Selberg class. Extended Selberg class meaning we don't need the Ramanujan hypothesis and the Euler product. So we have finitely many elements, AF. Now I'm not really describing what this AF is. This is after dropping that extra condition that we have, because it's a little complicated to describe. So I'm just going to say that there are finitely many elements in the Selberg class with this and with residue rho F. But the more interesting application is in the context of Dedekind zeta function. So I have written it in the following way, but I'll say a few more words about it. So if you have the same degree, conductor, and the residue, And let's say it satisfies this condition, the condition that appeared in the first theorem that I mentioned, then there are at most twice the degree number of Dedekind zeta functions. So this, however, this condition doesn't seem like it is often satisfied, because both sign as well as this rho f can get large, and this sign can become very small. But now once you drop this condition, we will get that there are some finite number of Dedekind zeta functions. So in case of Dedekind zeta functions, we only get finiteness. However, I believe that if you just give me the residue, I should be able to uniquely determine the Dedekind zeta function. Like for instance, if you just focus on quadratic Dedekind zeta function associated to quadratic fields, then the residue uniquely determines it. And I believe that should be true in general, but I don't have a proof for that. But more interesting case is, because we are looking at this general Dirichlet series, one can look at partial zeta functions, which so the number of partial zeta functions is the class number, and they also satisfy all the same properties, and they have the same degree conductor and the residue. And somehow employing this would give us some kind of a bound on the class number, because we will get how many number of such partial zeta functions are present. However, I'm not presenting it here because it is still baking, and once I have the thing sorted out, it will probably be available on archive. So one would expect to get an upper bound on the class number using this method. Okay. So now for the rest of the time that I have, about 17 minutes, I'm going to focus on the proof of the theorem. Now, about the proof of the theorem, I think the strategy that we use, again inspired by Burling, it seems to be a not very well exploited strategy. That's and I would expect that many more theorems can be proved using this method, and this is just one application. So here's the principle. The principle is, you take any general Dirichlet series where a_n's are positive integers, and then we translate it to a problem of infinite product. We translate a problem on general Dirichlet series to a problem on infinite products, and hope that that is easy to tackle. So let's say GS be given by this summation of n going from 1 to infinity an over lambda n to the s, where a_n's are positive integers. Define this function, this infinite product f of z, which is a product of n going from 1 to infinity 1 plus z square over lambda n square whole to the power an. Now a_n's are positive integers, so it's all well defined. And because this series is absolutely convergent for real part s greater than 1, we can conclude that this product is in fact an entire function. And now once we put squares here, it will give us that the product is an even function. So on the real line, whatever value it takes on the right hand side, same value it will take on the left hand side. Okay, so now we use the following identity. Integral of 0 to infinity log 1 plus x square dx over x to 1 plus s, given by pi over s times sine pi s over 2. Now this holds when the real part of s is between 0 to half. Now if we change variables x to x over lambda n, then we get the following. In the same region s between 0 to half, I get this on the left hand side, and on the right hand side, if I raise it to a power an, I get an over lambda n to the s times this pi over s sine pi s over 2. Now what we will do is we will just add this over n. Then on the right hand side we will get gs, and on the left hand side we inside the integral we will get f of z, f of x. And that's exactly what we will do. So this is what we have, but GS is absolutely convergent for real part of s greater than 1. So now we have to change our region where this is where this identity holds to be between, the real part is between 1 and 2. But for our use, this will not really do. I just I mentioned it first, because it is quite simple to mention. But what we need to do is we will have to look at z square over lambda n to the twice of df, where df is the degree is also an integer, so that's also positive integer, so it will all be fine. And ultimately we will have the following. So I will define the right hand side as this. So the right hand side then would become something of this sort. We'll have a s over, instead of s we'll have a s over df, and here we will have s over df, and we have gs. So notice that we had this condition that gs had trivial zeros on all negative even multiples of df. So that is precisely to cancel all the zeros, all the poles arising from the zeros of this sine function. So what we get is that this psi s can be analytically continued to the whole complex plane, because gs can be analytically continued to the whole complex plane, except for the poles at s is equals to 0. At s is equals to 0, we get a double pole, one coming from here and one coming from here. And at s is equals to 1, the pole that is coming from gs. So now one needs to do some careful bounding on the growth of this psi of s. This is which essentially follows from using Fragment-Lindelof theorem. So the Fragment-Lindelof of the theorem, not of strips but of arcs. So we would apply the Fragment-Lindelof theorem on this arc, and then we would apply it on this arc. And finally, what we get is, in this particular region, in the region R, this phi s divided by this particular term is bounded. Now, again, what we are using is we are using the growth condition that we had for g of s. Okay. And we also use this lemma, which is a property of the gamma function, not very difficult to show. Integral from -∞ to infinity, gamma of 2 plus 1 sigma plus 2 plus it is bounded by sigma cube of gamma of sigma, where sigma greater than 2. Now, using both these lemmas, we would obtain the following: that the integral of the absolute value of the psi of minus sigma over plus it, where sigma greater than 2. Remember that we had it on the negative axis. So this is bounded by this particular thing. So using both these lemmas. But what was our psi? If you remember, our psi was defined as a Mellin transform of this function f of x. So I can, so this was basically my psi after that divided by the df term. So what we have is this, if we take the Mellin transform, then we do have that for c greater than 2, log of f of x is given by this 1 over 2 pi I df integral over c psi of s x to the s over df. Okay. And once we move the line of integration to the left, because we know that the psi has poles only at 0 and 1, so we will get the following. Here log fx is just the main term, and this term comes from the pole arising from g of s at s is equals to 1, and these two terms come from the double pole arising from that s times sin s over df. So once we have all this, and now we already know some bound on this particular quantity using those two lemmas. So what we get is this log of fx minus some function of this particular type is less than this exponentially decaying function. Which, in other words, I can write this as log of fx over this and take exponentiation on both sides, and use the fact that e to the x is 1 plus big O of x, where x is less than 1. So I can say that f of x over this is just 1 plus big O of this particular quantity, because we are exponentiating this term. So what we have obtained here is that my f of x is very, very close to being this particular type of a function. And remember that we are in the region x is greater than 0 on the real line. X is greater than 0 on the real line, and f of x is very, very close to being a constant times x to the power of this times e to the this. Okay, so now we use a very nice application of Carlson's theorem. Let me remind you what Carlson's theorem is. So Carlson's theorem tells us that, okay, so what exactly are we trying to do? We are trying to say that if this happens, then we can pinpoint what the function f is. If we know that f is an entire function and this kind of a property happens, then we should be able to pinpoint what f is. And we use Carlson's theorem to do that. So Carlson's theorem tells us that if you have an entire function of exponential type, that means it is bounded by e to the k absolute value of z. And suppose we know that f has exponential decay on the whole real line, whether you go on the right hand side or the left hand side has exponential decay, then it must be 0. So any entire function cannot have exponential decay in both directions on the real line. So this is an application. Carlson's theorem is an application again of Ragman-Lindelof theorem. But one of the cute applications of Carlson's theorem is the following. It says that if you have, we have exactly two entire functions of exponential type, and let's fix f of 0 to be 1, such that your f of x, if your f of x looks like a to the x to the p minus e to the beta x on both sides, then there are exactly two candidates which satisfies this property. Now remember that when we defined our f of z was an entire function, but it was also an even function. So whatever happens on real part on x greater than 0, the same happens for x less than 0. So so this type of so if once we have this, suppose when we multiply this to the right hand side, suppose we assume suppose we have that this exponent is less than this exponent, which was precisely the condition in the original theorem, then we would get that f of x looks like this on x greater than 0 up to a term which is exponentially decaying, exactly what we have in this lemma. And then using Carlson's theorem and some very cute application of differential equations, one can show that if this happens, then there are exactly these two candidates for your f of z. And that is precisely what happens in our setting, and that is how we prove the theorem. Now let me just say a few words about how. So this is still assuming that that weird condition that we had, that alpha f is greater than equals to something. So, but if we don't enforce that condition, then the way we tackle the situation is, instead of saying that e to the x is well approximated by 1 plus we go of x, because this is less than 1, what we do is we just look at a larger expansion of e to the x, but because x is less than 1, we just look at 1 plus x square over 2 factorial and so on and so forth. We take it until a power of x such that that dominates this power of e over here. So a power of e here, which should dominate here, the power this, and then eventually we will get that f looks like not just one term, but several terms of combinations of polynomials and exponential. But it looks exactly like that on both sides of the real axis. We have to prove an analog of this lemma, which becomes slightly tricky, but it is possible to do that, and that is how we remove that condition. Okay, so that's all I have got to say. I think I am done before time, but I hope nobody complains. Thank you very much for your attention.
Thank you, Anu.
Yeah, thanks.
So, if there are any questions, so you can unmute and ask. Anybody can unmute and ask.
Excuse me, I do have a question.
Yes, Chacha.
Oh yeah.
Hi,
So in the context of the Selbert class,
yes.
Do you also consider the case when the dirichlet coefficients are not real?
So no, I mean, in fact, not just real. We have to force the dirichlet coefficients to be integers.
To be positive.
Positive integers, because you see, this ans appear in the exponent, right? Otherwise, we can't really make sense of it if these are not positive integers. So it is really requiring the positive integers.
Okay, so
yeah, so it's very restrictive. Yeah, so only application that you can hope to get is in the context of Dedekind zeta, where things are nice.
Yeah. So in the general case, then we might need like completely different method to tackle.
That's what it seems like. Yes.
I see. Thank you. That was very interesting.
Yeah, thanks.
So any other questions? So if there are no other questions, we thank the speaker.
So let me thank the organizers again and wish happy birthday to Professor.
Oh, there is a question. No, that's.
Anup.
Yes.
This is Srini.
Yeah.
Do you assume Euler product?
No, there is no assumption on either Euler product or functional equation. Nothing is required.
Yeah, because you were talking about partial zeta functions and things like that, right?
Yes, but
they
yeah,
but
yeah, exactly. So partial zeta functions will immediately go through because they're just some functions. But the key point for the comment on partial zeta functions is they all have the same residue, and that is what we are exploiting. That okay, they have the same residue, same degree, same conductor. How many of them are there?
Sure.
So that's
certainly,
that's the.
So Euler product and multiplicativity of ANs are not necessary.
Nothing is required. No.
Okay. Good talk.
Yeah, thanks.
So any other questions?
So, sir, can I ask a question?
Yeah, sure.
So, it is in the initial parts of the slides. So, where you are,
Yes, tell me. Yeah.
The condition that, so if you take the, so there is could you go to the initial slide?
Okay, so just tell me where to stop.
Yeah, this one only.
Oh, okay.
So, this first condition. So, instead of let's take the k equal to 1 case or whatever.
Yes.
This is a very restrictive condition, right? So first of all, I understand if it's a small epsilon.
Yeah.
It's demanding that.
It has to be exactly that growth. Yes, it is demanding that. Yes, that is right. Yes.
Isn't this condition very restrictive or like?
Well, see, but in principle, I think the growth condition is still far less restrictive than having functional equation. So you see, for instance, like when we so we really need to capture the exact growth. Otherwise, it is hard to say anything about the function. That's the point. So even in the case of Selberg class, if you just want to show that the degree it cannot be between 0 and 1, just growth itself is enough. You don't really need functional equation there. But it's a really restrictive condition. One has to I feel exactly captured the degree, not just the degree and the conductor. I also feel the implied constant here should play a role in better determining these getting better theorems in this context. Yeah, it is a rather restrictive condition. That is correct, but it is still just based on the growth of the function. Yeah.
So such classifications on zeta functions, are they like? Are there any similar results in the context of higher degree, for example, modular forms or such results?
For modular form,
you are telling about this converse. Okay, converse theorem you are telling.
Yes. Yeah. So okay, so the converse theorem, yeah, we know that like for instance, the Hecker's converse theorem tells us that for some cusp forms, if you have the same functional equation, it determines the exact L function arising from those cusp forms and so on. Yeah, those types of converse theorem. But the converse theorems that I was mentioning are basically the theorems where we are looking at the functional equation and trying to determine the function using the functional equation. So these are the converse theorems based on the functional equation. So the result of building is like you drop the functional equation, just look at the growth, and can we get some kind of a converse theorem in that context?
Okay, thanks.
Yeah, thanks.
Yeah, I have a small question, if I may ask.
Yes, please.
So are you? Are the degrees in your case are integers?
Well, all the examples that I know of are precisely the examples coming from Selberg class, or taking, like for Hurwitz zeta analog of things in the Selberg. For example, take the Dedekind zeta function an over n to the s, instead write an over n plus a to the s. So even in those cases, you know, the degree is a positive integer. I don't know of any other examples.
Yeah, no, not example, but in your theorem, you are kind of saying that.
So we are not, yes. In our theorem, we are assuming the degree to be an integer. Yes.
I'm wondering, can you take, I mean, what this technique?
Why do we require that? Again, because there is a power involved.
Like,
yes.
First question is like, can we take degree like an fractional and what?
Yeah. So that is I don't think so, because degree appears as an exponent. So it will be hard to define it. No, there will be a problem of defining the branch, choosing the branch of logarithm and so on. What one can do is, you know, instead of taking your ans as positive integers, you can take them as rational numbers, but where the common denominator have a bounded LCM or something. Yeah. That is possible, but otherwise it's.
Like conjecturally in Silver class, I mean, there does not exist any L function of fractional.
That is correct. But yeah, I don't think I can make a conjecture that degree should be integers here. I mean, per se, but the theorem that we are talking about is only when the degree is an integer.
Oh, yeah. So no, I was wondering. I mean, this technique, is it possible to modify in some way?
I don't
smaller degree.
I don't think so. Maybe some other technique would work, but not this exact thing.
Yeah, thanks.
No problem.
So if no other questions, then we thank the speaker. And we meet after 1 hour.
Excuse me, just
sure.
The class of function you have, you can add 2 of them, you still get 1 of them.
So the only issue that we will have is with the growth. It is unclear whether they will satisfy some growth, but it may so happen that you know, when in our growth condition we are saying that these dfs and alpha f's exist, but sometimes it may so happen that there is no such alpha f. You know, it might be an infimum of something. So that I think the existence of these two things may be problematic when we add functions.
No, but if you fix df and alpha f,
oh, then it is fine. Then it should be fine. Yes.
But then you can create infinitely many of them.
Oh, then also there will be a problem with this alpha f. Let's see. No, but of course not, right? I mean, if they have the same df and alpha f, they can cancel things out, no? So it could be a smaller.
Okay, I have to think about it.
So that so another thing that we have to I forgot to force this condition. We need to force the condition that the leading coefficient is 1. I'm sorry, I did not mention that. Yes. Sorry. That's a good point. Thank you very much. Otherwise, we could just take a constant times the function.
Yes. Okay.
Sorry.
Okay. Thank you.
Yeah. Thank you.
But the constants are allowed because you are only claiming fs equal to constant times theta s.
No. This is Hamburger's theorem. Sorry.
Okay.
In my theorem, they're exactly the same. But then again, if you multiply it by a constant, the residues will no longer be the same. I think the residue will take care of that condition.
Okay.
Like when you add things, then you know, the residues will differ. Will no longer be I think that this is to answer Professor Ramare's question. The residue will no longer remain the same. The growth will remain the same. But I also think that we need to take the leading coefficient as 1. At least that's what I use in the proof. Yeah. Thanks.
So thank you, Anup. So
Thanks,
we
thank you.
meet at 8:30.
Okay, yes. Thank you, everyone.
Thank you.